So yesterday we stopped while we were talking about diode characteristics. I think we covered the forward characteristics reasonably well, and then the reverse characteristics or the reverse breakdown operation is something we'll touch upon here, and then we will elaborate on when we move on to talk about diodes in more detail. Yeah. So you can actually operate in reverse breakdown mode with the diode, and what happens, and we call this mode of operation Zener mode of operation. So it's called Zener mode of operation, and basically it happens around your reverse voltage being equal to a value called Vz. Okay, and Vz is specified for a specific device. So, and there are devices that are optimized for different values of Vz. So you actually design them such that Vz takes on a number of values, right? So you can have the forward characteristic be like this, and then the reverse characteristic can have a Vz here, or a Vz here, or a Vz here, or a Vz here. What does this buy you? We will talk about that in an application like voltage regulation, for example, right? But it's possible to design diodes like this, and diodes that are designed that way are called Zener diodes. And I've put I put a data sheet for one of the Zener diodes on the class website, and this is one. This is a data sheet for a Zener diode that I opened up yesterday. And it's exactly like a diode. I mean, it's nothing. It's a diode. It's just that this VZ is optimized for different values. So it will have, for example, it will have a given power dissipation, for example, like this one has 1 watt power dissipation, still 2 terminals like every diode. But this family of Zener diodes, the 1N4728A all the way to the 1N4761A, gives V Zener voltages between 3.3 and 75. Right? So I can have voltages between 3.3 and 75 in the V Zener, as V Zener, right? So it's optimized for that. Regular silicon diodes are not. So there's a difference between a diode, a silicon diode that is typically used for forward current conduction applications and blocking in the reverse mode, and then there's diodes that are optimized. In this case, in the classical silicon diodes, they will have a low VZ. The VZ in that case will be between 5 and 7 volts, for example, right? But diodes that are optimized to operate as Zener diodes can have very large ranges of VZ values, okay? And so this is this set of diodes here, they give you VZ for many different values of VZ here, right? And they give it to you at a specific value of current, of course, right? So we have this so this value of this VZ here that we have is going to correspond to.
So that VZ value is.
Go ahead.
Is when the capacitor. Is that when the capacitor works, but in reverse bias?
Reverse breakdown, yes. This is reverse bias.
And what does that mean? That the current will go backwards, or what?
Yeah, this is initially here, before VZ, this was reverse bias, meaning what? Meaning that I had a higher barrier voltage, higher electric field, pushing minority carriers over. So basically what I have here, if I zoom in, here I have saturation current. This is this value of current. Remember, this is current. This value here, the value of current here at any point, is saturation current due to the reverse voltage polarity that you've placed across the diode, right? At some value of reverse voltage called VZ, the diode the diode current will start increasing considerably, exponentially, considerably and exponentially, right? So at some value, it makes sense at that point. You initially had an electric field that was pushing any minority carriers over the junction, right? If you increase that electric field, so increase the value of VZ, what happens? You increase the probability of these minority carriers being pushed over. So you keep increasing the current. So this current keeps increasing until a value called saturation current. At saturation current, at saturation, I mean, right before you, when you reach the value of Vz, you put so much reverse electric field. You put an electric field. You increase this barrier voltage considerably, that you are really sweeping a considerable amount of the minority carriers over. Right, so a huge amount of the minority carriers are now being moved over. After Vz, if V is beyond Vz, what happens, beyond meaning more negative than Vz, what happens is that, fine, you're pushing these minority carriers over, and they're going into the, if they're minority carriers on the N-type region, they're going into the P-type region, and they're actually breaking covalent bonds that are on the P-type side, they're on the P side. If you do that, then it's going to cause even more current to flow, right? So initially, these minority carriers were moving from the N side to the P side due to the electric field, right? You increase that, you keep increasing that, and it keeps increasing this phenomena. Keep increasing that and keep increasing this phenomena. But the carriers don't have enough energy to break covalent bonds on this side. So the electrons don't have enough energy to break covalent bonds on the P-type side, right? And the holes don't have enough energy to break covalent bonds on the N-type side. At some point, you've increased this electric field so much that you've accelerated. Remember, the velocity of drift is proportional to the electric field. The velocity of drift of the N, or the velocity of drift of the holes, is proportional to the electric field. Right? So at some point you will increase this velocity so much that it will the carriers will cross the junction from the N to P and P to N, and they will be breaking covalent bonds, and they will be accelerating current, and hence causing this increase in current to happen considerably. Right? So there is a region that's useful and reversible, and then there's a region that's not reversible. So the region that is useful and reversible is around Vz, and that's where we get the Zener operation. Right? And you can tune the Vz. Obviously, this Vz depends on the value of the electric field that you're going to apply. Right? So you can play with the size of the depletion layer, for example, to make sure that the amount of doping that you have, to make sure that are you going to have a wide depletion layer or a narrow depletion layer. We didn't discuss the width of the depletion layer. We skimmed through the width of the depletion layer last time, but it depends on doping. Depends on the way you dope the conductors, the semiconductor material. So you can play with that such that, fine, you have control over Vz. You can make this Vz high or Vz low at the point beyond which this current starts accelerating to a very high value. Right? So again, around Vz, it's called Zener mode of operation or Zener breakdown. Beyond Vz considerably, it's called avalanche breakdown.
And the avalanche is going down.
Avalanche, I mean, they're both going down. They're both current is increasing in both cases. But beyond a certain, so beyond a certain value of voltage, so in the neighborhood of Vz, if I zoom in here, in the neighborhood of Vz, this is acceptable. You can reverse the operation. But this is moving like this. So beyond Vz, so greater than Vz, with a reverse voltage greater than Vz, you get very high currents due to this avalanche effect. Okay? This is not reversible. It will burn the diode. Okay, so this is not reversible. You cannot operate in avalanche mode yet. So this is a summary of what I want to talk about here. And then these next two sections, 3.6, this section 3.6, I will skip. Basically, it talks about, okay, we've been talking about charges moving, right? Using what? Drift or diffusion, right? And storing charge in the depletion layer, and then recombination due to diffusion. We talked about that. This charge moving takes time, right? So anything that takes time can be represented or modeled as, a capacitive effect. So capacitances, you cannot change voltage abruptly across the capacitance, right? So what happens is, the voltage across the depletion layer, is it changed abruptly, or did we see this voltage, building up? We saw a plot where it was building up across the depletion layer, right? The voltage, this was V barrier, right, or V0, right? So this voltage was building up. So this this junction or depletion layer is like a capacitance, we said. And this is proof of that the voltage cannot change instantaneously across a capacitor. And the same thing here, voltage will not change instantaneously across a junction. It will take time. So it's like a capacitor. So capacitors have time-dependent changes of voltage and current across them. So you can model this change in the amount of charge in the depletion layer and the change in the amount of charge due to diffusion from both sides as capacitances, right? That's all this section means. I will not discuss. I will skip this section basically. But all of this stuff takes time, right? So if you want to change from forward bias mode to reverse bias mode, what do you have to do? You remember, forward bias mode is when you've collapsed the depletion layer to as small as possible. You've made the barrier voltage very small, right? Meaning what? You've removed the bound charges in the depletion layer. They've recombined with carriers from both sides, right? That's what you did. You decreased the size of the depletion layer, right? If you did that and you want to go from, and this is forward bias mode. How about now you want to go to reverse bias mode, complete blocking, right? What do you have to do? You have to increase the size of the depletion layer again, right? That's what we did. You know, remember the figure that we had about with these diodes? Right? So here, open circuit condition. And then here is reverse bias. Reverse bias, remember the depletion layer increased. We have more stored charge on both sides. Here, forward bias. We've decreased the amount of charge there, meaning we've decreased the barrier voltage as well. So we decreased the stored charge, stored charge and bound into the depletion layer, and hence we've decreased the barrier voltage, right? What this section is saying in 3.6 is that to go from here to here, right, takes time, because you have bound charges here that are going to recombine. How are they going to recombine? They're going to recombine with minority or majority carriers from both sides coming in, finding a vacant hole or finding a free electron, right? So it just says that, okay, this stuff takes time. That's really what section 3.6 says. I will not elaborate on section 3.6
And
further.
for it to be a forward bias, the positive has to be connected to the N-type,
For it to be forward bias, no, the positive has to be connected to the p-type,
P-type.
right? You're going to be helping the electric field. So we'll look at that a little bit more. Okay, so yes, go ahead.
Oh no, it's just,
You want me to put this thing again?
yeah,
Okay, here.
no, because now it makes sense. So when it's forward bias, it basically decreases that depletion zone, so it makes it easier for
Yes.
um,
Diffusion to happen.
for the fusion to
Yeah,
happen.
it makes it easier for diffusion to happen because you have less electric field. You've opposed the electric field generated by the barrier, by the junction, right? So by the barrier voltage, basically.
And what is reverse bias?
Reverse bias means you have increased that barrier voltage. You've increased the barrier voltage, and if you increase the barrier voltage, you increase the electric field, meaning you would increase the drift, but you would reduce diffusion considerably. But we said drift is very small anyway, so if the drift is very small, diffusion you've minimized using the reverse bias voltage, then you've basically created a condition where no current is flowing, theoretically speaking, except for leakage current, for example. Okay?
Okay, thank you.
No problem. So that's basically the summary of slide, section 3.6 in this chapter, in this text, version of the text, which talks about this capacitance. So it talks about the junction capacitance and it talks about the diffusion capacitance. So there is a time required for holes and electrons to diffuse from one side to the other, and this is modeled as a capacitance since the voltage due to that will change with time. It's not abrupt. And similarly, for you to go from a wide depletion layer to a small depletion layer, meaning remove the bound charges or put in more bound charges, it takes time, and they model that as a capacitance. That's really all they're saying here. This will become important when we talk about devices, power device, MOSFETs and BJTs later, because for you to start conducting, you'll have to charge or discharge a depletion layer. It will take time. So they will model that as a capacitance in the equivalent circuit. Yeah. So that being said, so that wraps up this discussion, and we will talk now more detail about diode from an application perspective. Okay. So this is chapter 3 in your textbook. Okay, this is chapter. So the stuff we were talking about was the end of chapter 1 in your textbook. This is chapter 3 in your actual textbook. Yeah. Okay. Now, diodes. We said, we looked at their characteristics, and we said that these devices are, have an interesting characteristic that looks like. That looks ideally like what? Sorry. Ideally, if so we have we had a p-n junction here. This p, this was n, right? Ideally, we said that we either forward bias or reverse bias, right? If I'm forward biased, then what am I able to do? I'm able to conduct current, right? And if I'm able to conduct current, I will say that I was able to sort of collapse the depletion layer, ideally speaking, right? I was able to overcome the barrier voltage, right? We had a barrier voltage that was blocking my diffusion, right? And if I'm able to overcome that, then I'm able to conduct current. So assume this barrier voltage is very small. If assuming it's very small, ideally 0, then I have a characteristic of the diode in the forward condition that looks like this. As soon as I have, a V voltage equal to, in the forward direction, equal to a very, very small value, I can conduct an infinite amount of current. And we said that this amount of current should be limited by your external circuit, right? And if I'm going to put any value of negative voltage, then I'm going to block any current from flowing because I've increased the barrier voltage and prevented diffusion from happening, right? And this is the ideal characteristic of the diode. This is like modeling the diode as in this case here, as a short circuit. So this is my diode here. In this case, forward case, model it as a short circuit. And in the reverse case, it's an open circuit. It's blocking. I is 0 for any value of V that is negative. Okay? And this is the polarity that I'm referring to. This is V diode. This is V diode. I diode.
So on the left side it acts like open?
Yes, this here it's acting like an open circuit. This is reverse. Here it's reverse. Forward. This is the ideal characteristic. We said this is fictitious, and we will add here when we overcame the depletion layer voltage and were able to diffuse the carriers, that voltage had a value. And this value we said was about between 0.5 and 0.9, or typically we will use it at 0.7. We will say that there's a value here, 0.7, that we will sort of assume that this is when my diode will start conducting. Only when my anode here versus the cathode is 0.7 volts higher, the current will start conducting. So this becomes, this was my ideal characteristic, the blue. The green becomes sort of what is called the constant voltage drop model of the diode. And in the negative, as soon as your voltage on the anode decreases beyond 0.7, then you block.
What's that point called again?
This one?
Yeah.
It's fine. Technically, it's called the cut-in voltage. Cut-in. It will come. It will be introduced later, but it's called cut-in voltage. It's the voltage beyond which your diode will start conducting it. And then we said that there's this abrupt thing, this abrupt movement is not abrupt characteristic from no conduction to conduction is not realistic, and really what's happening is fine, current will start moving, but how does it start to move? It rises exponentially. So we said that there's an exponential rise associated with this abrupt ideal sort of model of
It's the point where the voltage will
Here, it's when you were able to, using your external circuit, to overcome the barrier voltage. Right? You have a barrier voltage that was reduced using a external forward voltage. Both of these together cause the barrier voltage to diffusion to decrease. And you were able to start conducting current by diffusion. But diffusion is dependent on concentration. And concentration, we saw that concentration for, if you're going from P to N, here I have a lot, here I have a little. So it looks like an exponential. So since the concentration looks like exponential, hence diffusion current exponential, since this is mainly diffusion current, and this is guided by, can be modeled as an exponential. Okay, that's in the forward. And in the reverse, we said that beyond a certain value Vz, which is still a safe value, beyond that with a certain amount, depending on the diode itself, you will still be able to use the diode. And this will also look like a sort of an exponential here. Beyond Vz, with a certain amount, in the vicinity of Vz, you can utilize this diode, this characteristic, and go back up and down. Remember here, we can go up, current can be high, and current can be low. How is this going to be governed? By your external circuit. How is this governed by external circuit? For example, I have a 10 volt power supply here, and I will put a resistor, and exactly. So it will depend on the value of the resistor. So this is 1 kilo ohm. Then here it's a higher voltage with respect to, this is the anode, this is the cathode. So the anode is at a higher voltage with respect to the cathode, right? Which means that the diode will start conducting. But how much current is going to flow here? It's V divided by R. This will happen to be 10 milliamp. Is this safe or not? I don't know. You have to look at the diode datasheet. Specific diode datasheet, calculate, either they will give you the maximum current or they will give you the power loss. Right? Yes.
And in that diode that you showed us, the VC value was less than.
Yeah, because this is ground. This is zero.
No, remember the specifications you showed us for the diode?
The data sheet?
Yeah. What was the VC value on that one? Do they show it?
The VZ, yeah. This one, it's a family of Zener diodes. This is a family of Zener diodes that has VZ between 3.3 to 75. So remember, I said that there are diodes that are, typical classical silicon diodes that you would buy for, a signal processing application, are not Zener diodes. They would have a Zener voltage. I don't have a classical, a regular silicon diode datasheet, but we also said that there's a family of silicon diodes that is optimized to have various values of Zener voltage. Again, remember, we said the Zener voltage, the value of the Zener voltage, what happens at the Zener voltage? We said at the Zener voltage, the electric field that you've created in the reverse direction, remember, when you put reverse bias, the device, that you are doing what? You are aiding drift, right? You are opposing diffusion, right? You are aiding drift. But if you aid drift considerably, that's the effect of this Zener diode. That's this V-Zener effect. So you're able to optimize your design of the diode to aid or to control the value at which this V-Zener effect happens. V-Zener effect is when you've aided the minority carrier transport across the junction considerably to be able to increase current, right? Because we said that saturation current is low. Saturation currents are low. Here I push so that it's almost zero.
What's the amount of the Zener voltage?
It depends on the diode. So for classical silicon diode, between 5 to 7 volts, right? But sometimes you want to operate here. It's nice. Do you like operating here or not?
No.
Why not?
That's the best.
This is what you want to do, actually. You want to allow conduction, and then you want to prevent conduction from happening. So this is nice. You like this area.
You don't want it to reach infinity.
No, of course you don't want it to reach infinity, but you want your diode to be able to conduct or block. You want that. That's what you want to do. You want to create the ability to alter the condition in the circuit, right? Why, we will see some applications next, but you like this, right? Also, you may like this, because this is also nice. You were applying a certain voltage, and then current was zero. Then you apply a little extra voltage, current increased in the opposite direction. Right? So this may be also nice.
So instead of
Instead of
going
operating here, you can operate here.
but that will make current go back, go opposite.
Exactly, it will make current go in the opposite direction. I agree. That's fine. It's fine. It's okay. It will make current go in the opposite direction. You may want to have that. You may want to use that. What the benefit that gave us is that we found that we are able to control the value of VZ. Okay, this barrier voltage we were not able to control. This was around 0.5 to 0.7, 0.8. This was a fixed value, right? So in the forward direction, I have this fixed value of forward voltage. In the reverse direction, because it's not diffusion based, it's drift based. It's a different phenomena that's causing the current to increase.
Wouldn't that defeat the purpose of a diode though? If you wanted to, if the current, if you reach that, then it goes backward.
But it depends on, again, where is VZ coming from? From your external circuit. You have to be smart on what you design externally and connect your diode in, right? So it's, electrical engineering is for smart people, right? So you have to make sure you put your diode around, stuff around your diode that will make it operate the way you want it to operate. So if you have a circuit that's outside this diode that's going to make it operate in forward mode and reverse mode in a way that you want, then it's okay. But if you have something that's going to make it, you want to operate only in forward mode, and your circuit is putting negative voltage across your diode, then it's your mistake. You need to be able to know the constraints of your design, right? So because the diode, it's a diode. It's not smart. It does whatever you tell it to do.
No, but like in the diode itself,
Yeah.
here is like where we find the 0.7 value.
This is
On
the
the
forward.
diode?
In the forward.
Yeah, is it
in-
on the diode?
Of course, across the diode. Yeah. When it starts to conduct, you will see that. If you put an external circuit and you are able to overcome the barrier voltage. Overcoming the barrier voltage meaning what? You started conducting, right? When you start conducting, this diode is responding by, a minimum of 0.7 volts, opposing you, right? This is like a voltage that, remember, you have to make the anode at least 0.7 volts higher than the cathode. So this 0.7 volt is like a 0.7 volt DC source opposing current flow, right? But VZ, we found, again, in the reverse operation, we found that it's not, we are able to control VZ. I can play with the doping and the size of the, the N-type material or P-type material to be able to see, to be able to utilize this Zener effect to my benefit. Zener effect utilizes drift of charge to create current. So if I am able to utilize that in a nice way, then I can also operate in this area. I want to create devices that can block and conduct. And they're in response to a forward voltage. Wow, I can also create this, I can also utilize this device to block and conduct in response to a negative voltage. So it has some nice features. But the limit is, this is not a large window. The V-Zener is a small window. And it will depend on the device that you've utilized. So the Zener datasheet that I put on their website has many, so they create a Zener diode for 3.3 volts. If you go to 3.6, the current will increase too much. So they created another Zener diode that is optimized with a VZ of 3.6. Another one with an optimized VZ of 3.9. Applications of this we will see. But they've, you can play with that. That's all I'm trying to say here. Okay. So we talked about, reverse bias, forward bias. Forward bias meaning device is turned on or just on. Reverse bias, the device is off or set to be cut off. So these are just some terminology that they're using in the text in electrical. Some terminology that we will use. So we will utilize many of these different terminologies. Let's look at a nice application before, so that we can sort of become motivated a little bit on why we want to do this, right? So we discussed this ideal characteristic, and this is one application of diodes, right?
Halfway rectifier.
Exactly. So it's a halfway rectifier. So you take 438?
No, for the lab.
Which lab? Here?
Yeah, I don't lab today.
Ah, today's lab. Yeah, okay. So the half-wave rectifier is in one application of rectifier. So we said of a diode. So we said that we would like to operate. Sorry, the way we would operate the diode is if I'm able to place a more positive potential on the anode versus the cathode, then the diode would conduct. Right? So in a circuit like this, if I put an AC sine wave here, sine wave, consider you have some ground reference, right? So you have a ground reference so you have positive voltage with respect to ground, and you have negative voltage with respect to ground. So if this is confusing for you, if an AC sine wave is confusing, just remove this, forget about this being a sine wave. Just assume it's a DC source. And this DC source has positive values with respect to ground, and this is ground, or it has negative values with respect to ground. Right? So if it has a positive value with respect to ground, then this node
That's how it works.
This node is the most positive voltage in the circuit. This node is the most negative voltage in the circuit. Since this is the most positive node in the circuit, and this is connected to the anode of the diode, then the diode would conduct. Ideally, it would look like a short circuit when it conducts. Ideally. Right? Ideally, it would look like a short circuit. In practice, or practically, if I want to utilize the more complicated model, not exponential model, a more complicated model included what? We included this 0.7 volts that opposed the operation of the diode, right? So I will later I will add this 0.7 volts this way. It will be a voltage that opposes the current to flow, right? So only when the input voltage becomes higher than 0.7, right? Isn't that what we said? Only when the input voltage becomes higher than 0.7, so this minus this should be higher than 0.7 for the diode to start conducting, right? We will look at this later, but since we talked about it, I might.
So why is it a short circuit?
Because this is the ideal model of the diode. Ideal model of the diode is like this. This is V diode, and this is I diode. The ideal model, we said, is like this.
We said
In the forward conduction, the V is 0, and the current can increase, and it will be limited by your external resistor. So that's why when it's forward, I modeled it as a short circuit, since V across it is 0, and the current through it will be limited by my external circuit.
I thought it's like black
What?
and we came back.
In reverse?
Yeah, it's a short
No. In reverse, the V, you have a V value. Here, I have V values, right? Here, I don't have. Here in forward, I have V0. As soon as I have 0 plus 0.00 whatever, 0 plus voltage across it, then I can conduct current theoretically to infinite amount of value.
short.
Basically a short circuit, right? So that's why it's modeled as a short circuit when it's forward biased.
But that has, the input voltage has to be greater than, for example, the 0.07.
The voltage will have to be greater than 0.7 practically. If I use that model, but if I use the ideal model, this is my ideal model. Ideal model has, as soon as the voltage is positive, it will conduct. That's the ideal model.
That's why it makes the halfway, because it won't conduct at negative.
Exactly. So as soon as you flip this source, so that the voltage here is more negative with respect to this being more positive, right? Then the anode voltage will be the most negative voltage in the circuit. If this is the most negative voltage in the circuit, that means on the cathode side it's something more positive than it, right? Which means that the diode will block. It's operating here.
And it's blocking it.
It's blocking it, meaning, and ideally it's an open circuit. If it's an open circuit, then the V output is equal to 0 since no current will flow, right? So what is that going to do to the output waveform? When I have positive voltages, I am placing my input across the output resistor. When I have negative voltages, I have an open circuit. So the output voltage will look like this.
This one when the diode became an open circuit.
V output. Here, this is the diode open circuit. Output voltage here is 0.
But like it has to be negative, has to be
the negative, again, remember what happened here was this source is now, I'm in the negative, I'm in the second half cycle. Second half cycle, this source is negative here with respect to this node,
Like
which
here,
means this is negative. All of this is the most negative. So the anode is seeing a negative value. Yeah, yeah, it's like it's a sine wave input. So it's like putting a positive DC supply and then putting a negative DC supply.
But here, like they didn't change the sign.
I know they didn't change the sign, but they drew it as negative. You remember in power in electronic in circuits, you always used to assume a polarity, and if your calculation gave you something opposite, then it's a negative. So here they drew here's your calculation. It gives you a negative. That means I can flip this source. You either make this source look like this, positive, and don't change its polarity and just say that it's negative, or you flip it, right?
I think the symbol's like kind of confusing because if they would put an AC, it would have been a little bit easier. But
Some people will get confused if they put the AC. So I like to just put DC sources, and say, okay, at this point in time, what do I have? I have a positive voltage. Okay, draw your positive voltage here, and your diode here, and your resistor. How about at this point in time? I have a negative voltage. Then draw a negative voltage, and draw your diode here, and draw your resistor. Okay, so now here is the most positive value in the circuit. Then, which means that this is more negative. So the diode will conduct. Here, this is the most negative value in the circuit, which means that on the other side, it's going to be more positive. So it will block. So you can do it that way, this way, whichever way. As long as you... So this is an application of the diode, right? And it's a non-linear operation of the diode, right? It's either on or off, right? So this is a non-linear application of circuits, right? I use this to create another waveform. What's the new waveform versus the old waveform? This was an AC waveform, right? Has an average value of 0. How about this waveform?
wouldn't it be RMS?
This has an average value. This has an average value,
Oh,
right? Remember, if I want, what is power? Power in a DC circuit is VDC times IDC. These are average values of voltage, average values of current in a DC circuit. So this, if I have a DC load here, if I put a DC motor, fine, a resistor may not be very interesting here. But if I put a DC motor would like to see an average value of voltage to produce an average value of current to produce an average value of torque.
and AC it can't.
Well, AC it can't. It will just be doing this. Right? It will just be jumping back and forth because there's no average value of current, voltage and current. Right? Okay, so this produced a waveform with average value. Your laptops, your cell phones, these are all batteries, right? Batteries like to be charged, they're DC. They want to be charged with an average value of current, right? So for you to plug it in here, you have to put a rectifier in the middle. This is the most basic rectifier, okay? In 438 we study the more advanced ones, we will skim through them here, but we study more of that in 438, how to design those in more detail, right? But this is the most basic application of that. So I've created a waveform with an average value from a waveform with no average value. Is this a nice clean DC? No, it's not. It's a huge bumpy DC. It has a huge peak-to-peak ripple, right? This is ripple. This is an average value. This is a waveform with average value, so it means it's a DC waveform, but it has huge ripple on it. Go ahead, sorry.
Oh no, I was just gonna ask, would the peak of the voltage DC be the same as like the peak of the AC? Not like the complete.
Not if we leave it this way, but if we add a capacitor here, we can do that.
So the blue graph is the AC.
Yeah, the blue graph is the input AC, and the red is the output, but without the capacitor, just the resistor. Okay, we will do capacitor later, but for now, just the resistor.
It represents the open circuit and
What represents the open circuit?
the
The resistor?
the red graph.
The red graph represents the output voltage, V output. So it includes the full operation of this circuit in response to the sine wave.
So not the one.
Both. So this. Okay, you have an output when the diode is short circuit. What are you doing? You are placing your input voltage across your output resistor. So what do you see at the output? You see the input voltage. So here, this and this are identical. This blue waveform here, which I now made red, and this red waveform here are identical. They're exactly the same, right? For this positive half cycle. For the negative half cycle, the circuit is open. What are you putting across the output? Nothing. You're putting 0, so the output is 0, right? So this is, but you've produced a waveform with an average value. This is one application. The rectifier, this is called a rectifier. And more technically, it's called a half-wave rectifier. Why? Because it rectifies half the sine wave only, right? So this is one type of rectifier, the simplest type of rectifier. And this is, rectifiers are one of the main applications of diodes, especially on the power side, power conversion of, adapters, motor drive, all power applications, they will have, similar requirements for something like this, yeah. But what we saw here was, we benefited from the diode's nonlinear characteristic, right? On and off, right? Another application, not power, is digital circuits. So another, digital circuits will also benefit from the diode's nonlinear properties. So if I want to create an OR circuit or an AND circuit, I will see that I can create that using diodes. How do I do that? So let's look at what we have here. They're saying that this is one of these is an OR gate and one of these is an AND gate. You've taken 248 gates, right? No? 248. Okay. 248? Okay. OR gates is, okay, me or you will go out the door. AND gates, me and you have to go out the door together, right? So it's, if you, from a digital logic perspective, an AND gate, if you have a 0, so it's, digital systems are operated, they only understand 1s and 0. 1s and 0 is not, 1s and 0 volts. It's actually one voltage level and another voltage level. It can be 0 and 3.3. It can be 0 and 1.8. It can be 0 and 5. It can be 1 and 5. It's up to you as a designer. But typically, in current digital systems, digital IOs, mainly on processors, would be maybe 0 to 3.3. 0 for low voltage, for a low, and 1 for a high, it would be about 3.3 volts, right? So basically, we use zeros and ones only, right? So if I put a 0 and 1 in an AND gate, the output is 0. So an AND gate, so input A and input B have to be 1 for me to get a 1 at the output, right? So input A and input B have to be 1 for me to get a 1 at the output. If they're not the same, then you get something different. If you get 0, 0, you still get 1, right? If 0 and 0, you still get 0. 1 and 1, you get 1. So both inputs have to be 1. So one input A has to be 1, and input B has to be 1 for you to get a 1. Otherwise, you get a 0. So that's an AND. So let's look at, this is an AND using diodes. So here I can put plus 5 volts, or I can put 0. Here I can put plus 5 volts, or I can put 0. Here I can put plus 5 volts, or I can put 0. If I put plus 5 volts at VA, what's going to happen? Is this diode going to conduct?
No.
It will not, because we said that for the diode to conduct, the anode has to be higher voltage than the cathode. So now I see 5 volts here, and I see 5 volts here. Right? If I put a 5 volts here, right? If I put 5, here I see 5, here I see 5, assuming there is no current or little current. Here I see 5, here I see 5, this diode will not conduct. How about if I put 0?
It will conduct.
If I put 0, it will conduct. Conduct meaning it looks like a short circuit. Short circuit, and here I have ground at 0, right? What does this do to the voltage at this node? It's 0. I mean, this point is connected to this point now, right? So 6 is different, right? So 6.
You're always going to do it to that voltage source?
They all have to be the same. Sorry, go ahead.
No, I think you just...
No, I will do it. I can do it. This is the AND gate. So remember, what does the AND do? all of them have to be 1. All the inputs have to be 1. So input A has to be 1 and input B have to be 1 for you to produce a 1.
So VA
If they are different, 1 or 0 and 1, then the output will be 0. So now, if I put 0 volts here,
zero,
0, 5, 0, for example, right? So this is like the 0, 1, 0
yes, so
here.
no.
So the output will always be, output is this Vy here. This is going to be 0. But if I put 1, 1, 1, or 5 volts, 5 volts, 5 volts in this case, since I put 5 volts here. If I put 5, 5, 5, this diode will not conduct. This diode will not conduct because it's not seeing a higher voltage here than here. It's seeing the same.
And
Right.
then the Vy will be 5. If they
And VI
Vy in that case will be 5. Yes, sure.
result is-
and
So,
if
how
all
is it gonna be five if it's on the first place? It's like in the opposite side. Didn't you say it's like the first example of figure eight?
Because there's no current flowing. If I have 5 here, for the diode to conduct, I have to have voltage here being more positive than the voltage here. But if I put 5 volts here, and I put 5 volts here,
It'll be the same.
there's no difference between them.
okay, what about
So,
0,
so not to conduct.
The same.
0, 0, 0. Anytime you put a 0, it's here you're putting 0, and here you have 5.
And that
That
will
means the
go to
diode will conduct. As soon as one of them conducts, it connects this node to ground. As soon as this node connects to ground, then Vy is 0. So as soon as any of them are 0, this node's output is 0. That's why Va and Vb and Vc have to be 1 for you to get a Vy equal to 1. Right? So that's an AND circuit using diodes. How about OR circuits using diodes? So here it's the same. So here I have a resistor connected to ground. I want to see what's happening at my output. So here I can, if I put 5 here,
It's gonna be-
and I put 0 here and 0 here. So this is more positive than this node, and
And the whole thing will be 5.
it will conduct, and I will get Vy equals 5, regardless of this being 0 or 5.
Because that other node's gonna be 5.
I don't care what these others are. As soon as I have 1, then that's an OR gate. OR gates,
أول شيء نشوفه
OR gate is the output of an OR gate is 1 anytime if you have input A is 1 or input B is 1. Right? So the OR gate, and if both of them are 1, you also get a 1. Right?
no what is it
If both of them are 1, you still get a 1. That's the OR gate. Right? That's OR gate. So when you take 248, you will know this. I mean, this will be clear, but this is from a circuit perspective. If I put 5 here and a 5 here, fine. This will conduct and this will conduct, and this node will be at 5. Assuming, of course, there's no circuit, more details, right? But
okay if the first one is 0
the first one is 0, and the others are what?
no 5 0
5, 0. You tell me.
If it's 0, 5, 0,
Yeah,
it's gonna be 5.
it's still going to be 5.
so it doesn't matter
Yeah. The OR gate, again, the OR gate, as long as I have one input that's 1, the output will be 1. Okay? The AND gate, both of them have to be 1 for me to get a 1. So this is an example of
when all of them are 0
when all of them are 0, then you get a 0, right?
if all of them are 5 we get 5
Of all of them, if any of them are 5 in the OR gate, you will get a 5. So if all of them, that's fine.
إذا كلهم 0 so we get 0
If all of them are 0, you get 0. Okay?
so in an OR gate we have 0 and 0
If in OR gate, you have 0 and 0. Here, it's like these are all zeros. What do you get? This will not conduct, and the output will be 0. You don't conduct.
That's pretty clever.
Because the output is, why is it? So because the output is connected to ground through this resistor. If there's no current flowing, then the voltage here is equal to the voltage here, which is 0. Current will only flow when the diode becomes forward biased.
What happened if we take the resistor off?
Then you have what is called in digital circuits like a floating point. you don't know what the value of the voltage is. You always have to define your voltage. That's where you as a designer need to make sure your circuit around the diodes is a good circuit. Right? If you don't do that, then it's your mistake. It's not the diode's mistake. Right? Blame it on the diode, yeah. So anyway, so this is another application. So you see, we saw two different applications: one in digital domain, one in power electronics domain, right? So, and then we will see another another application of this is in an amplifier domain. So,
No, but
right.
like
Yes, ma'am.
in this case, we can just use diodes or not? Like, can we use something else instead of diodes?
No, you can use something else. We will study how to make. I think we will study. Yeah, we will study how to make these logic gates using MOSFETs.
Can you use a diode as a feedback or an op amp?
For the feedback, yes, you can. We will have circuits like that to do certain functions, right? And I think in chapter 7, they have, so they start talking about funky applications with diodes, and then they refer you to chapter 7 to do even more funky stuff with it. So
What would that do? Wouldn't that just act like a regular?
it will again, it will be able to with different functions. I mean, there are many different types of circuits, right? So let's get to that. Yeah, we will be able to, in amplifiers, you were clipping because of the voltage, for example, right? With if you add diodes around the op amps, for example, you can clip, you can block before you start clipping due to the gain. You can do stuff. So we will look at circuits like this, and then there's a whole chapter dedicated to even more circuits like this, combining op amps and diodes that we will not cover, but I will briefly refer to you. Anyway, so this is another application of diodes that I wanted to demonstrate to you. And I'm not going to go through this example. Example 4.2 is a nice example. It's very straightforward, okay? It just tells you, okay, so what, assuming the diodes to be ideal, find the value of I and V in the circuits. You want a quiz now? That's fine. I mean, quiz for a homework quiz? I don't know. Yeah, you have, the homework has similar problems, yeah. But basically here, they're just telling you to calculate the values of currents and voltage. So they want the voltage here, and the voltage at the output, for different values of resistors. Here is 10, here is 5. Okay, so the way you would go about this is here you can assume this is a plus 10 volts, right? And this is a minus 10 volts. So it looks like this may be conducting, and this, if this is conducting, then maybe I have 10 volts connected all the way to here. If 10 volts is connected here, maybe I'm blocking this. So you will assume different. So you will assume a situation where you're conducting and you will calculate. So you will assume a situation where you're blocking and calculate. It's a straightforward example. I will not go through it. So please go through it. Yeah. But the math is not difficult. It's very simple, straightforward. So and there's more of this digital logic circuit stuff with calculation of currents. I mean, we went through it as a concept, but here you would calculate the actual currents and voltages, etc., given certain numbers. Okay, so now let's look at. So we talked about the diode characteristics a little bit. Here they zoom in a little bit on, for example, the origin here. Remember what was happening as soon as I start placing a reverse bias voltage. In forward bias, if I have a small forward bias voltage, means what? It means I have a high. I still have a high voltage barrier to diffusion. Only when I'm able to decrease that voltage barrier to diffusion am I going to start current conduction. Right? That's in the forward condition. How about in the reverse condition? In the reverse condition, as soon as I have a negative voltage, what's going to happen? Electrons will start, minority carriers will start drifting and creating a current, right? And that's why I have a small jump here. As soon as I have a negative voltage, I will have some current. Right, so they talk about that a little bit, and then they talk about the characteristic in more we discussed the characteristic in quite a bit of detail. So the forward operating mode, and we said fine. There's a cutoff voltage beyond which this exponential starts rising, and they range it between 0.5 to 0.7, 0.8. Right, there's no specific value. We will typically use this value here as 0.7, the point where the current starts rising significantly, We will take that as 0.7 in a lot of our analysis. But it's not a fixed value. If you go to a power diode, it may be a little bit different, right? But generally, for our analysis, we will start by 0.7. And I will show you what we will do to be able to get a better estimate here. So here they talk about the different zones. So in the forward bias region, the voltage drop across the diode is positive. And it has to be greater than the cut-in voltage, and typically around 0.7. In the reverse bias region, the voltage across the diode is negative. And in the breakdown region, the voltage is less than or more negative than the Zener breakdown voltage. Or ZK means the knee. They call this the Zener knee voltage. Knee means like this looks like a knee, somebody's knee. So they call this the Zener knee voltage. And there will be a corresponding Zener knee current, right? So they like the human body. Electrical engineers, the relationship with biomedical engineering. Okay, bad joke. Sorry. Okay, so now we will elaborate a little bit more on the. So we want to be able to start solving circuits in more detail with these diodes and look at exactly what's happening to currents and voltages. And at some point, not only use the diodes as switches on and off, completely nonlinear. How about maybe operating in the linear region and using that as an amplifier? We will see the application of that. Right? So to do that, we have to look a little bit more about on the modeling of the diode. So we said that in the forward region. So let's look at. Again, I'm not going to derive the equation, right? But this is the equation for current that governs all the way. So if this is voltage of the diode, this is current through the diode. And this equation covers everything from, I didn't draw it very nicely as a smooth exponential, but
Everything above the knee.
yeah, right before the knee. So this equation will cover that. So if the voltage is 0, what do you get? I is equal to what? If the voltage V, small v, if V is 0, this is 1, so 1 minus 1 is 0, right?
It's V divided by VT.
Yeah, it's V divided by VT. So if V is 0, I'm at 0, right? The current is 0. How about if V is negative? What's e to the minus x? E to the minus x goes down. If V is negative and a little bit, not very small, so it's almost 0, right? It's fine. E to the minus x approaches 0 if the V goes larger, negative larger. So let's say we are at reasonable values of negative V. At reasonable values of negative V, this approaches 0, right? And the current I is equal to minus IS, right? Which is the saturation current, right? This is a negative value and it's negative IS. We agree? So does everybody see this equation, what it's doing? So this is the exponential function that governs the model. It's a model. You tested this device, and in the lab you will do this characteristic, I believe. So you tested this and you fitted an exponential to it. This is what it looks like. And it happens to also comply with the physics, right? So that's the nice thing about this stuff. Okay, so this is the model of current in the forward bias region. That's fine. And we will see that this current depends on V over VT. VT, if you remember, is the thermal voltage that we talked about quite a while ago, and it depends on the diffusivity versus the diffusivity of the charge versus the mobility of the charge. So the diffusivity so basically the constant that controls the diffusion of the current versus the constant that controls the drift of the current. Yeah, mobility. So it's diffusivity over mobility. That was VT. And remember, this was temperature dependent, right? Mobility was temperature dependent. So which means that VT was temperature dependent, right? If it depends on a temperature dependent variable, then it's a temperature dependent value, right? So it is a temperature dependent quantity here. So, and it's another way to fit that into with the physics, and again we will not derive that, but another equation for another way to represent Vt is kT over Q, where K is a material dependent constant, T is the temperature, Q is the charge of the electron. It makes sense. It depends on temperature. As long as it depends on temperature, we're good. Right? It's a constant that depends on temperature. It's called the thermal voltage. We called it the thermal voltage before. It depended on temperature because it was diffusivity over mobility. Right? So it depends on temperature. That's what they're trying to tell you here. And it has, if you do the numbers, and you calculate Vt at room temperature, it will be about 25 millivolts. Why is this important? Because later we will approximate. We will always use. We'll typically use Vt as 25 millivolts, and look at where we are on the current characteristic curve. So given now that if you know Vt, you just have to assume different values of V. If you know Vt and you know Is, because you know the saturation current of the device, and you can sort of draw the value of current that's through this diode. Yeah. So that being said, so we can stop here. I think it will not be possible to continue. So we'll stop here and we'll continue tomorrow then.